Welcome back. This is part 5 of this series on coupled oscillations. We are going to again apply the formalism that we presented in the part 2, and we are going to apply it to a specific example of molecular vibrations. In fact, this is a topic of intense research over many decades, where you can identify molecules by actually measuring the vibrations. So there are all sorts of techniques which are called spectroscopic techniques, like infrared, Raman, and so on, and neutron scattering, that can be used to measure the vibration. So there is intense research in that area. If you want to know more about this, actually, you can check out some of my recent research talk that is on my YouTube channel. But the point here is to go back to applying the theory that we've put together and understanding the vibration in molecules. And we are only going to look at one molecule, carbon dioxide. And I will conclude this screencast telling you a little bit about the role of carbon dioxide as a greenhouse gas. But before we go there, it's maybe a good idea to stop and a little bit maybe contemplating the problems with degrees of freedom. So in principle, if you have a three-dimensional object and you have n particles that are not constrained by anything, so for example, the rigid body is a constrained situation, but let's imagine that you have n particles that are not constrained. So obviously, if you have three dimensions and n particles, the total number of degrees of freedom will be 3n. So you expect to have 3 motions. However, and here I'm referring to the first line of this table, I mean the second row of this table, out of all those motions, 3 of them will be pure translation, which of course do not oscillate and do not correspond to a vibration. In addition, 3 will be rotations, right? Because we have 3 dimensions, we can have 3 independent axes of rotation. So that gives me 6 degrees of freedom that are already taken away by the translation and rotations. So that means that the number of vibrations we can have will be 3n minus 6. You will understand what I mean by additional vibrations in a few moments for the last row. So that's the last column. So the 3n minus 6 is the typical number of vibrations we have in 3D. Now imagine we have a situation where all the atoms are collinear, like on a chain, and we are actually going to study the chain next. So when we are on a chain, we still have three translation. There is no problem. However, we are losing 1 rotation. So the rotation with the axis which is parallel to the axis of the molecule has no effect on the molecule. So you have to think about, like, you have a chain and you rotate it along the axis, makes no difference. So this is not a degree of freedom because there is no way to tell the structure, the difference between the structure with and without that particular rotation along the axis. So that only gives us 2 rotations. So in that case, when you have a collinear atoms with n particles, the number of vibration is actually 3n minus 5. Okay, so this is very simple arithmetic. It's actually very good to do this to make sure we are at a good place. Now imagine that we confine the particles on a plane, and we have n particles. Of course, the number of translation on a plane will be 2. Clearly, the number of rotation on the plane is just 1. Right? It's just like the polar coordinate. It's just one rotation. So that means that in this case, the number of vibrations in plane will be 2n. Remember, we have to use 2n since we work on the plane, minus 3. So 2n minus 3 will be the vibrations in plane. So now what's interesting to do is to see that the difference between 2n minus 3 and 3n minus 6, which is the general case, is n minus 3, right? And so those n minus 3 will be the remainder vibrations, which will be the vibrations which will be the out of plane vibration. Okay. One thing that's going to be particularly interesting to us is this last case, the last row, which we are going to study more in this screencast, and it's related to the linear molecule. so it lives in one dimension. The number of translation in that case, if we impose a system to live in a one-dimensional space, is obviously 1. The rotation will have no rotation because again we live in a thing that the system is imposed to stay in a tube, if you will, that it cannot rotate, and of course the number of vibrations will be n-1. N because we have one dimension with n particles, so n-1. Now, obviously, no molecule or no object lives in 1D, so the remainder of the total vibration has to be compared to the third row of this table, right? The linear atoms in 3D, and that means that we are going to have 2n-4 transversal, so in other words, perpendicular to the line of the atoms. We are going to have 2n-4 additional vibrations. So we divide by 2 usually because the 2 directions that are perpendicular to the linear molecule are equivalent, so that they yield the same vibration. So the same frequencies and models. So that's usually what we do. Okay, so this is actually a table that's very useful to understand, and I invite the reader to make sure that you understand this and can calculate it. It's really about bookkeeping. It's not super complicated, but it turns out to be very important because when we study actual system, it's always a good idea to know what's the size of the solution space. We've looked at that already when we were looking at the secular equation and the determinant. Obviously, in order to get any chance to get the right result, you need to at least know what's the dimension of the space you work with. Otherwise, there's absolutely no chance. So let's have a look at an example, which is going to be the carbon dioxide. Carbon dioxide is actually a linear molecule, right? Unlike water, H2O, which is actually like a triangle. There is an angle because of the valence electrons, obviously. But carbon dioxide is actually a linear molecule. It's shown on the left. We have a mass in the center, which is carbon, and 2 other masses, which are oxygen. And the bond length is B, right? That's the same. It's a symmetric molecule. Now, what we are going to do in our treatment here, we are going to say that the potential between the atoms is going to be approximated by a quadratic potential, just like we did in our formalism. Remember, the Taylor series is stopped at the quadratic term. This is equivalent of saying that we are modeling the bond as springs with force constant kappa. Kappa 1, in this case, in this picture on the right, is essentially the strength of the bond, of the chemical bond. So we have 3 molecules. We have a collinear molecule. So we go back to the previous table, and we see that we have 2 longitudinal vibrational modes. So remember, n-1, 2 longitudinal vibrational mode, and then n-2, so 1 transverse vibrational mode. So the longitudinal is along the molecule, and the transverse is perpendicular to it. So it turns out those 3 vibrations, we can separate the longitudinal and transverse mode because they do not interact with one another. And it makes sense, right? The transverse mode vibrates along the x-axis, and the transverse mode along the y-axis, I mean the vertical axis, and of course those motions are orthogonal to one another. So we will be able to do this. Okay. Now we want to make sure that in our treatment we are going to get rid of the center of mass. Get rid of the translation, the pure translation, which means that we can fix the center of mass. If we fix the center of mass, then of course no translation is possible. And we do that so that we do not end up with translational results, even though we are looking for vibrational ones. I'm going to explain that from a dimensionality point of view momentarily. So again, on the left-hand side, these are the coordinates of the center of mass. Well, we should divide by the total mass, but since we want it to be equal to 0, this expression there is basically saying that the x position of the center of mass has to be equal to 0. So that allows us to eliminate one variable. X1, X2, X3 were the displacement of the two oxygen and carbon. So we had three degrees of freedom. Now, by eliminating one of the variable, for example, X2, we only have 2 degrees of freedom. And it makes sense, right? Because the 2 degrees of freedom will yield the two the two longitudinal modes, sorry. So from a dimensional standpoint, this is good that we do that. So this is going to be what we do for the longitudinal mode. And we are going to do the same for the transverse mode, but this is for the longitudinal mode. And you can tell that by the fact that we are using X, which is the horizontal coordinate along the spring. So let's have a look at the longitudinal mode. And once again, we are going to use the same business as we've done so far. The exact same everything that we have done so far using the formalism. So we have the same business as before. We have to calculate the m's and the a's, which are respectively the coefficients for the kinetic energy and the potential energy. So that's always the same stuff. So it's a good application. So let's look at the kinetic energy. Of course, kinetic energy is given for the rectangular coordinates x1, x2, x3 by these terms. We know that there is actually a constraint on x2 because we fixed the center of mass. It's what we just did a few seconds ago. So we can replace x2 dot and we obtain very straightforwardly this term here. Now, this term, it's fine. You can actually solve everything here using this approach, and I actually encourage you to try to do that. However, here, the approach that is being used in the textbook that we are using, I try to avoid using a non-diagonal M matrix. And so for that reason, they try to get rid of the terms like this, because those dynamic coupling are going to yield off diagonal terms in the M. I actually strongly encourage you to try to treat it this way. This is going to give you the same result, just the determinant will be slightly more complicated, but really not that much. The reason why I say this is because what we are going to do now is to do a change of variable to get rid of that term. The problem with change of variable is something that's always very intimidating to students, because you say the student is like, how did the professor know which change of variable should be made? Well, it turns out the professor usually knows because the professor reads the textbook, not because it came as an inspiration. So people actually, when you solve it, can in a raw form, like using the formalism that we've done so far, without changing a variable, I mean, those things become obvious, which change of variable you can do, but you can only say that after the fact. In any case, let's close this parenthesis and follow the procedure that's done in the book, which is a change of variable, so that we get rid of the dynamic coupling. And the change of variable is actually pretty straightforward. We come up with the generalized coordinate q1 and q2, which will be related to the sum of x3 and x1, and the difference between x3 and x1. If we do that, we can rearrange x1, x2, x3. Remember, x2 is simply it's really related to the x2's value is imposed by the fact that we are fixing the center of mass. And so if you use these numbers, pretty elementary, you can calculate the kinetic energy again by doing a substitution x1, x2, x3. And when you do that, you end up with this shape, which is somewhat complicated mass terms in front of the derivative of the generalized coordinate. But the good news here is that we did get rid of the dynamic coupling. So that makes the M matrix diagonal, right? Remember the M matrix that we've used so far, so much. Now, after the kinetic energy, we need to evaluate the potential energy. And remember, the potential energy is just that one of a collection of springs that we have here. And very straightforward, the kinetic energy, the potential energy, sorry, is just the sum of the contribution for the elongation and compression of the two springs. And that compression of the first spring will be x2 minus x1, and the compression of the second spring will be x3 minus x2. Actually, I say compression could be elongation if the numbers are negative and positive, obviously. Well, in this case, the change of variable is very handy, because remember that the change of variable we decided to use is reminded here on the top right corner of this slide. And then, of course, the potential energy is also actually just terms with Q1 square and Q2 square. And there is no cross terms. There is no coupling, Q1, Q2. And the reason why there is no couplings is because we already did the change of variable that gives us the normal coordinates, really. That's the reason. Again, it seems to be coming out of a hat. If you were to do the full calculations instead, you would find that you would actually find the normal coordinates as part of the eigenvectors analysis of your problem. But in any case, you must be very happy at this point because both t and u are diagonal, will be expressed as diagonal tensor. And so what we do, we end up with this determinant, as I just advertised, it is diagonal. Now, students like this because a diagonal, when you have determinants diagonal, it's actually very straightforward to calculate the vibrations, right? I mean, it's the normal mode, the eigenvectors, the eigenvalue as well. And then you find the solution that are given on the right-hand side. So this is actually very easy. This is the beauty of using a diagonal expression, of course. So that's nice. Now, what's nice is that, of course, the normal coordinates are already the Q1 and Q2, right? Since they diagonalize this matrix, and so we can write directly that the A12 and A21, so the off-diagonal term of A's, are zeros. And so indeed you see that the normal coordinates eta1 and normal coordinates eta2 are just proportional to Q1 and Q2 by choice. Okay, so that's very nice. Now, the usual approach is that to understand a motion for a particular normal coordinates, we set the other one to 0 and we see what happens. Okay, and so you will see what happens in this case is that, remember that Q1 is related to x1 plus x3, Q2 is x1 minus x3. So these are really motion that really are related to this difference. And then when you analyze those modes like we've done before and straightforwardly from here, we find that we have two modes. We have a mode where let's look at the second mode, is the easiest one first. In the second mode, the carbon atom, so the big atom in the center does not move. Right, x2 equal to 0 is the second row of the table, and the other atoms are actually moving out of phase towards it. So this is kind of a symmetric situation. In fact, it's anti-symmetric really in this case. But the point is, it has a high symmetry, and so the mode that we find is square root kappa 1 over m, which is exactly the frequency you would get for spring. And it's not surprising since here we essentially have two identical springs that are attached to a fixed object, which is carbon. It just happened that way for this mode. This is not the case for mode 1. For mode 1, the carbon atom is moving, and then we have an in-phase move of the two oxygen. And that corresponds to a higher frequency, and so it is typically the case that we have the much higher frequency here when you involve the motion of the three atoms. So that's very nice. We will come back to them in a minute. Now let's have a look at the transverse mode. Well, the beauty of the transverse mode is that by our dimension analysis, we only have one. So we expect that if we have a determinant to calculate, it will be a 1 by 1, which is frankly a very easy one. But the hard part for the transverse mode is actually to write the kinetic energy and potential energy. It's not hard, but it's the hardest part. So let's do that. We are going here. We look at this particular plot here, and then you see the three atoms now are transverse, so they are allowed to move out of plane. Now, one thing that you need to take a moment to think about is that we are actually removing rotations. Okay, so we do not want a rotation to take place because as we said, we are treating the pure rotations and translations separately. And so for this particular molecule, the only way we can have vibration perpendicular to the axis of the molecule is that y1 and y3 move in, they move the way that's written, that's put on the plot, they move in phase. If they did not move in phase, they would correspond to a rotation. And then, as we said, we do not want a pure rotation in our system. On top of that, so y1 equal y3. And it has to be opposite to y2. And the reason why it has to be opposite to y2 is because we remove the translation. So very easy. We just do this as we did before. We look at the center of mass coordinate along y, and then we obtain this result here. This is the usual formula to find the y component of the center of mass. And that value has to be equal to 0 because we want to avoid translation as well. That imposes y2 to be that value here, minus small m over big M times y1 plus y3. And we see that the motion y2 is out of completely 180 degrees out of phase from y1 and y3 because of the minus sign that we have here. Okay, so the funny thing is that we have 3 coordinates, y1, y2, y3, but we know that we only have 1 vibrational degree of freedom. So we have to get rid of, we have to impose some constraint. And the constraint, we just did them, is that the y1 equal to y3, so we get rid of 1, and y2 is the value that's on the slide. So we actually have only one variable, which is y1, and y2 and y3 can be obtained as a function of y1. So we are, in terms of dimensional analysis, we are in good shape. So I really strongly recommend that you do always a dimension analysis. This is the best way for you to know that you are still on track. So now, what we decide to do, now we have to do is to find a normal coordinate, generalized coordinate, and instead of using a y as a coordinate, we are going to use the angle alpha that's shown on the plot, on the figure. And what we usually do for alpha, we say we can calculate alpha, and we are going to suppose that we have a small angle oscillation, so we always look at very small oscillations so that the Taylor series expansion is still valid. And so we say that we are going to approximate the tangent of alpha by the sine of alpha. And remember, b is the distance between, it's the bond length, right? And then when you do that, so the horizontal part, when you do that, you can see that alpha is obtained from the tangent, and you can see very easily that the tangent is equal, alpha is equal to that number for small oscillation. I strongly recommend that you pause the screencast at this point and draw the triangle in the figure on the top left and convince yourself that alpha is this value. This is actually the hardest part of the entire screencast, is to convince yourself that alpha is that value. At least it was for me. So that allows you to write alpha as a function of y1 only. Remember, we only have one coordinates, one variable, since y2 and y3 can be expressed in terms of y1. Now we do the usual stuff. We do the kinetic energy, and of course, if we use alpha as the generalized coordinate, it's like the kinetic energy is that of a rotation. So it's like a rotation in polar coordinates, so something that we've seen many times. Well, this one would be the kinetic energy that we have used in general, but if you do the substitution, you end up with a kinetic energy equal to this value, and it depends on alpha dot. Makes sense, again, for one variable. And as I said, this kinetic energy looks like a kinetic energy in polar coordinates. It does look like that because it is exactly that. Okay, excellent. We can do the same for the potential energy. And the potential energy really measures how far from a straight line the system goes away. So it doesn't like to be too bent, but it does because of the vibration. And so you have to pay a potential energy. So potential energy increases when you have a bend. And of course, the bend is the arc circle, which is sustained by the angle alpha. And that arc circle is, of course, B alpha. And we can actually say that the potential energy is like a spring that's related to the presence of B alpha. So B alpha, as I said, is the arc that's related to the out of line deformation. And of course, if we have no deformation, that U is equal to 0. That's alpha equals 0. So you can see that there is only one variable, as I said many times, alpha and alpha dot. The velocity, the generated velocity. So calculating the determinant is very straightforward. So these are the two things that we have. And well, you can get it right away, right? So you get it right away using the formula we have. You can do the one-by-one determinant if you want, but you get directly the vibrations, the vibration like this. And kappa 2 is essentially the oscillator strength of the deformation out of plane. And so what we see in this case is that we can actually write the y1, y3, and y2. Now, before we conclude this screencast, I like to tell you one more thing. We have seen 3 vibrations, right? 2 in plane, 2 along the line, and 2 and 1 that was transverse. So if you try to remember how they look like, imagine that carbon dioxide, because they are not the same chemical element, there is a slight charge transfer between the atoms. And so that charge transfer actually creates a dipole. In fact, they create 2 dipoles along the bonds. And you can see that out of the 3 vibrational modes, only 2 of them have a net total dipole that's not equal to 0. Actually, if you remember the anti-symmetric motion when carbon does not move, that one, the 2 dipoles are opposite, and no matter what you do during the vibration, the total dipole is 0. Why is that important? Well, because if you radiate those the carbon dioxide with an electromagnetic wave, like light, for instance, the way that the coupling happens physically is that the electric field of the electromagnetic field does interact with the electric dipole. That's the main interaction that we have. Of course, if there is no electric dipole, there is no interaction. So it turns out that you can excite carbon dioxide with light. So basically add vibration to your system, if you will, only for 2 of the modes that I showed. So the one where the longitudinal one when carbon is moving, and the transverse one. Actually, both of them correspond to a net dipole. And why is that important? Well, it's because it happens that the energy that the oscillator, so the carbon dioxide in this case, the energy that it absorbs from light is going to be related to the energy of vibration. So you excite vibrations and then you add energy to your system. And as you know from thermodynamics, adding vibrations increase temperature. And this is exactly what happens in the greenhouse effect. So you have some vibrations that actually right in the energy range, in this case infrared, so that it absorbs the energy reflected by Earth. So that's something that I like to say. And again, I'm going to conclude on this slide, which is, you will notice that it's a slide that's actually picked from another course that I teach, which is thermodynamics. This slide here shows that carbon dioxide does absorb light reflected by the Earth, by the surface of the Earth, in this infrared region. And there's 2 frequencies. The reason why we have 2 contributions is for those 2 vibrations. So we don't have 3 because one of them does not have a dipole moment. However, this greenhouse effect can also have a very good beneficial effect. It turns out, this process, not the global warming, the process itself. Because of its higher temperature and black body radiation, the sun emits mostly in the UV light. Not mostly, but there's a big peak in the UV light. If the Earth was to get the entire UV content from the sun, we would not have life as we know it on Earth. In fact, what happens is that there is a big chunk of this UV radiation that's actually stopped by the exact same mechanism as the one I just showed you, but by ozone, so O3 molecule. And so the ozone molecule actually had the vibrations and a much higher energy, and so they can actually absorb this UV light. And it's what actually makes it possible to live here. So you see the 2 same physical process, one makes life possible and the other one is causing global warming. So that's why it's very important to understand science before we can make any conclusion about what science tells us and what science can't tell us. Thank you very much for your patience and your interest in this series of screencasts. I will have one more screencast on this series, which would be the loaded string, and I hope to be available soon. Thank you very much.